Have you ever actually stopped to wonder, how did the AI get good at this? Not, what does it do? We've covered that. But how did it learn to do it? Who taught it? What did that process actually look like? And why does it work at all? Because here's the thing. Nobody sat down and programmed ChatGPT to write poetry. Nobody hand-coded the rules for recognizing a face. Nobody explicitly taught any of these systems the skills they have. They learned, on their own, from data. And the process by which that happens is one of the most fascinating and counterintuitive ideas in all of computer science. Here's the problem with teaching a machine anything. Modern AI models have billions of parameters. Those tiny dials we mentioned in episode 1. GPT-4 has an estimated 1 trillion of them. You can't adjust those by hand. You can't write rules for 1 trillion variables. There is no programmer alive who could look at that system and say, this dial should be 0.0034, and that one should be minus 0.7821. So how do you tune 1 trillion dials to produce intelligent behavior? You don't tune them at all. You let the model tune itself. In the next 4 minutes, I'm going to show you exactly how that works. And I promise, by the end, you'll have a mental model of AI training that most people, including a lot of developers, couldn't explain clearly. It starts with a concept so simple it almost feels like cheating. Think about how you learned to throw a ball as a kid. Nobody gave you the exact equations for trajectory, wind resistance, and muscle force. Instead, you threw it, noticed where it landed, adjusted slightly, threw it again. Each attempt gave you feedback. Each piece of feedback led to a small correction. After enough corrections, you could throw accurately without thinking about it at all. AI training works on exactly the same principle. The model makes a prediction. It checks how wrong that prediction was. It adjusts slightly to be less wrong next time. It repeats this billions of times. Here's where it gets beautiful. The way the model measures how wrong it was is called the loss function, a score that tells you how far off the prediction was. A high loss means very wrong. A low loss means getting closer. The goal of training is to make that loss as small as possible. The technique for doing that is called gradient descent, one of the most important ideas in all of machine learning. Imagine the loss as a hilly landscape. The model is a ball sitting somewhere on that landscape. Training is the ball rolling downhill, always moving in the direction that reduces the loss, always seeking the lowest point it can find. With each step, the model adjusts its parameters slightly, nudging 1 trillion dials a tiny amount in the direction that makes the loss go down. Step by step, correction by correction, the model gets less wrong. But here's the part that makes it work at scale. When the model makes a wrong prediction, the error signal doesn't just fix the last layer. It travels backwards through the entire network, all the way to the beginning, giving every single layer a tiny nudge in the right direction. This process is called backpropagation. It's the engine that makes deep learning possible. Without it, training a network with hundreds of layers would be completely impractical. Think of it like a game of telephone in reverse. The error at the end whispers back through the entire chain, and everyone adjusts their behavior slightly based on what they hear. Now put it all together. You feed the model a training example. It makes a prediction. You measure how wrong it was using the loss function. You run backpropagation to send the error signal backwards. Every parameter gets a tiny adjustment. You repeat this with millions, sometimes billions, of examples. Early in training, the model is essentially guessing randomly. Its predictions are terrible. The loss is enormous. But after enough iterations, enough throw, adjust cycles, the parameters settle into a configuration that actually works. The model has learned, not because anyone programmed the answer in, because it practiced getting it wrong until it got it right. Full honesty moment, it's not perfect. Gradient descent has a famous problem. The ball can get stuck in a small valley before finding the true lowest point. In machine learning, we call this a local minimum. The model stops improving because every direction seems to go uphill, even though a much better solution exists somewhere else on the landscape. Modern AI training has clever techniques to avoid this. Adjusting the step size, adding randomness to the process, training on data in a different order each time. But it remains one of the fundamental challenges in the field. Even the training process has to learn how to train better. So what does this mean for you? It means that every AI tool you use is the product of an almost unimaginable amount of failure. Trillions of wrong predictions, each one leading to a tiny correction. Each correction compounding over months of training on servers the size of warehouses. It also means that when you give feedback to an AI, thumbs up, thumbs down, a correction, a rating, you're contributing to the same process. The model learns from you, in real time, the same way it learned from its training data. Your feedback is a data point. Your correction is a gradient. And it means you should have realistic expectations. A model trained on mostly English text will be better at English tasks. A model trained on mostly formal writing will struggle with informal conversation. The training data shapes the intelligence, completely and inescapably. Loss functions, gradient descent, backpropagation. A trillion dials adjusted a trillion times until something extraordinary emerges from the noise. That's how AI learns, not by being programmed, by being wrong over and over until it isn't. Next time we're going to zoom out and ask, what actually makes one AI model better than another? Why does GPT-4 outperform GPT-3? Why do some models excel at code but struggle with creativity? The answer has everything to do with scale, and it's going to surprise you. Subscribe so you don't miss it, and we'll see you in the next one.